Hello, this lecture is going to be a review of thermodynamics that we started at the beginning of this year. So if you remember, we discussed the flow of energy, which is what thermodynamics really covers. When we first started it, we were looking at flow of energy from one substance to another. And as we move along in this unit, we're going to be looking at the flow of energy to form and break chemical bonds. But let's get a review back of kind of the flow of energy, the initial thermodynamics that we started off at the beginning of the year. So let's kind of review energy. So energy really is that ability to do work. That's what really the definition of energy is. It's measured in joules or calories. Conversion of that is 4.13 joules per calorie, though typically we will look at joules as kilojoules. And calories could be as kilocalories as well. One of the important concepts that we want to focus on is law of conservation of energy, which really just states that energy cannot be created or destroyed. It can only be converted. It can be moved from one thing to another. It can be changed from kinetic energy to thermal energy, but the amount of energy stays the same. Now, one of the things when we were talking about energy, we really can't measure the total energy of anything. We can measure the amount of energy that is moving, though, from, say, the system to the surroundings. So it's kind of redefined system. That's kind of the thing that we're focusing on. So that could be a chemical reaction. That could be a piece of metal. If you remember, we did some calorimetry work, which we'll talk about in a second, where we looked at the amount of energy. We could measure the amount of energy being moved from the system into the surroundings. The surroundings then is everything else, the stuff that is surrounding our system. The systems that we're focused on, surrounding everything else. So we can measure that using some specific apparatus to look at that change. So let's talk about Q equals MCAT. If you remember this formula, Q is the amount of energy, M, I put that on here, is mass, C is specific heat of the material, and that has a unit usually in either joules or calories per gram degree Celsius. And finally, delta T is change in temperatures, which is our final temperature minus our initial temperature. And we use that if we know the mass and we know the specific heat of the material, which is always specific for every substance has a different specific heat of a specific heat. And we know the change in temperature. We know how much energy has been moved, how much what the energy change is. So when we talk about the measurement of that, we did that early in the year. We talked about calorimetry. Calorimetry was using a calorimeter to measure the change in a temperature of a liquid, surroundings, as energy is transferred into or from it. So let's look at an example. Let's think about go back in the Wayback Machine, and we think about we took a unknown piece of metal and we heated it up in some boiling water, and we knew the temperature of that boiling water. So we knew the temperature of the hot metal. We put that hot metal into our calorimeter, which was a big kind of metal cup that had water in it. We knew the initial temperature of the water. And so the heat from that metal eventually heated up the water that was in that cup, and we could measure that change in temperature of the water. We also measure the change in temperature of the metal. So if we know the mass of the water and the mass of the metal, we can figure out how much energy was flowed from one thing to other. So conservation of energy tells us that the amount of energy that came from the metal and flowed to the water is going to be equal. So we're going to have this, the amount of energy transferred does not get destroyed. It does not change. It just, all we're doing is we're calculating the movement of that energy and how much energy moved. So we can use MCAT for the metal. So if you know the mass of the piece of metal, you know the initial temperature of the metal, which was going to be really, really hot. You know the final temperature of the metal, which was the final temperature of the water. We can determine the specific heat of it because we know specific heat of water is 1 calorie gram degrees Celsius. If you know the mass of the water, because we typically measured it, and we know the initial temperature and final temperature of the water from the experiment, we can do the calculation and figure out that we can figure out the specific heat of the metal. Similarly, if you're missing any variable, we could do that calculation. So remember, it'd be MCAT of the metal equals MCAT of the water. So the next thing we talked about way back in this, I think it was like our real first unit, was phases of matter. So this is the state of matter, whether it's a solid, liquid, or gas. So if we want to think about energy-wise, solids have very low amount of energy in their particles. The particles aren't really moving. They're close to each other. Really, we think about that as they're kind of just, as the energy is being added to those solids, it just vibrates faster and faster until eventually it can become a liquid. So liquid has the particles have a higher amount of energy than the solid does. The particles that are able to freely move around each other, but are still kind of in close contact with each other. They're not flying off in different directions as we see with a gas. So gas has the highest amount of energy. The particles there are not in contact with each other, and they're freely moving, flying all over the place, filling up the space that they can. And that's what we studied that in our gas laws unit. So when we think about phase change, we can look at this graph here on the right. If we are looking at the amount of heat versus temperature, we can see that there's not just this solid single straight line, that we get these breaks. So as even a solid or anything is changing temperature, we get an increase or decrease in temperature depending on which way whether we're freezing or melting. If we get a change in temperature, at some point we're going to hit what we call our melting point. That's the temperature at which that particular substance melts. So for water, pure water would be 0 degrees Celsius. And if you remember from our heating curve of water lab, we took ice, and we really had just ice water. And we slowly started to add some heat energy to it through a Bunsen burner or a hot plate. And the temperature took a while to change. And if we remember from our observations, we still had that temperature stayed kind of in a flat at that melting temperature at 0 degree, or right around 0 degrees, as long as there was some solid in there. As soon as all the solid disappeared, all of it melted, and we all of a sudden became liquid, then we started seeing a change in temperature as our liquid heated up and approached our boiling point. So, and we hit that boiling point again for water, it's 100 degrees Celsius. So we hit that boiling point, and it started to, that temperature flattened out again, and then would increase if we had the ability to measure once all that water disappeared and we had the ability to measure the gas temperature, we would have seen that it would have continued to increase. So these flat points on the graph are our phase changes. So a phase change is where the temperature doesn't change, but the energy, as you can see here, the heat or energy is increasing or decreasing if we're pulling it away. And that energy goes into, if you're melting it, it's going into breaking those kind of intermolecular forces that we've talked about in our previous unit, and kind of loosening those up so that the solid can have those molecules moving around more freely, breaking that structure, the solid structure, into a liquid. And then once the liquid goes up to a gas, we're breaking those intermolecular forces even more so that they can form the gas. So if you remember, we want to talk about endo versus exothermic processes. The heating is an endothermic process because our water is our system, and it is absorbing what energy is going into the water. And as we're cooling, we're getting an exothermic reaction because even though the water is getting colder, the surroundings are absorbing the heat. They're actually getting hotter because we are not changing the overall amount of energy. But focusing on that particular system, they're either absorbing or releasing energy. So absorbing energy, endothermic. Exothermic is releasing energy. It's exiting the system. And lastly, let's talk about quick calculations. So again, we can still use Q equals MCAT anytime that temperature is changing. You just got to remember that the specific heat of that particular substance will change depending on whether it's a solid, liquid, or gas. With water, it's 1 calorie per gram degree Celsius for C as a liquid, but it's much different, much lower as a solid or as a gas. And then finally, to get into phase change, since we don't see a change in temperature, we can't use MCAT because there's not a change in temperature, it stays flat. So we use this thing called Q equals M delta H, where delta H is the heat of fusion or vaporization. And that's basically the amount of energy or heat needed to melt or vaporize a mole or gram of that particular substance. So that does change whether it's a solid. If you're going from solid to gas, or solid to liquid, that is a certain specific delta H. And as you go from liquid to gas, that's a different. Depends on what the substance is, and that's always can be found in charts all over the place. So that's a quick review of what we covered in way back in our first month of school. So we kind of got through really kind of half of our thermodynamics way back then. And so now our next step is to go into the thermochemistry, the chemistry of the study of energy flow as bonds are broken or formed. So look for that video next. Thanks.